Hello, my name is Peter Pizzo from Imperial College London, and I would like to present the work that we've done in Work Package 5 in the CloudButton project. So what is Work Package 5 about? Well, it is about serverless programming models. So while we've seen quite a lot of previous research in serverless computing looking at storage, scheduling, big data, machine learning, state management, and so on, there have been far less published work looking at serverless computing from a programmer point of view, so thinking about programming abstractions that support the implementation of applications using serverless computing and function as a service. So what we want to do in this work package is fill this gap and think about the programming models that we expose to programmers. In particular, we need to satisfy the requirements that come from the CloudButton use cases in terms of the programming languages that are needed. So in particular, we need support for Python and Jupyter notebooks, for Java, and also for languages such as C and C++. And so in Work Package 5, we've done work to support all of those languages, and we've explored different approaches how these languages can be made compatible with CloudButton and both support the implementation of new applications as required in our use cases, and also support the porting of existing applications using a lift and shift model. So how does Work Package 5 fit within the work package structure? Well, it is supported by the other work packages, so in terms of the infrastructure abstractions and also some of the state management work that we've done in Work Package 4. So just to give you a specific example how the work in this work package has been informed by the use cases. So for example, we have the Genomics use case, and here in the Genomics use case, we're dealing with an existing multi-threaded implementation in C. And so we don't want users to have to rewrite this particular application, but instead we want to directly be able to take this code and run it on top of the CloudButton framework. And this is something that we've achieved using the Faasm approach, and I'll talk more about this in a moment. Okay, so what's the structure of Work Package 5? Well, we have task 5.1 that looks at programming abstractions for stateful serverless computing, and there I'm going to talk about Crucial and the idea of cloud threads. We have 5.2 that looks at consistency and fault-tolerant models, and there I'll discuss how Faasm enables different levels of consistency and fault tolerance. Then task 5.3 looks at programming tools for porting existing applications. And here I'll talk about the OpenMP support that we've developed. And then finally, 5.4 looks at more general application patterns and libraries for real-world applications. And here I'll talk about our work on supporting MPI. Okay, so let's start with task 5.1. So here we've worked on Java support for CloudButton, and in particular the idea is to establish a new abstraction of a cloud thread. So a cloud thread is similar to a regular thread that any Java programmer would be familiar with, but it is something that can then be executed in a serverless environment. So we provide a class cloud thread that wraps this abstraction, and then different executor services that can now run those cloud threads across a Faas platform. And at the same time, there is support for shared state that is associated with this thread. And this is done using regular Java facilities, so regular collection types that any Java programmer would be familiar with. And a particular interesting feature of this API is that it also is built around using annotations to, for example, denote specific shared state or other concepts. And this is something that is quite intuitive for Java programmers to use. So this is an example of how the Java Crucial API would be used. So in a client application, you would simply create a new cloud thread, and then what this would do is it would actually run in a Faas environment and then have access to a shared object store that then manages all of the state that is associated with this thread. So this is a solution that is specific to Java. We've also adopted a similar approach providing Python support in CloudButton. And so here the idea is that we follow a very popular API, the Multiprocessing API in Python, that many developers are already familiar with, and we provide a serverless version of this. So we take advantage of the existing abstractions such as a process, which is a basic function entity that can be executed in the cloud, a pool of processes, and then we have various communication and synchronization objects. So again, this is something that a Python programmer would be aware of, and so that makes it quite easy to take, for example, existing Python code and port it to then execute using CloudButton. So here is an example of what the Python multiprocessing API would look like. So in a client application, you create a new process, you start that process, and that process then is scheduled and run in the serverless environment. And again, it can execute remote access to a shared key value store, so in our case Redis, to then manipulate objects. Okay, so this is a brief overview of some of the programming abstractions that are language specific that we provided for Java and Python. But another challenge that we had in the project in some of our use cases that we had to support existing code. So here we had to take ideally existing implementations written in low-level languages such as C or C++ and then wrap them in a way that we could execute them in an existing serverless environment. So actually, when we try to do this using today's state-of-the-art technologies, there are various challenges. So one challenge is the isolation overhead, so just the cost of doing this. And then the other problem, when you look at legacy code, it wants efficient state access, and this is something that cannot be done easily with existing Faas offerings. So in our work, we've overcome those problems by adopting an intermediate representation for the implementation using WebAssembly. So WebAssembly is a lightweight, memory-safe language. It's increasingly being used in the cloud environment, and it has significant benefits over, for example, standard isolation mechanisms for serverless, such as containers, in that it achieves a lower isolation overhead, and it also gives you very fine-grained control over memory accesses. So our idea for using WebAssembly to take existing legacy code and porting it to serverless is by sharing state in a way that combines a local tier, where we are sharing state between functions that execute on the same worker, with a global tier that then synchronizes that state across different workers. So we've implemented this approach using a system called Faasm, and Faasm is open source and available on GitHub. And so it is implemented around this abstraction of a Faaslet. So a Faaslet is the unit of computation that is being deployed and run by the system. And Faaslets have access to those shared memory regions. So this is how they can cooperate and share the same state. And then there is a global synchronization mechanism that can then synchronize locally available state with this global state tier. We also have a mechanism for very quickly instantiating Faaslets using proto-Faaslets, which are essentially snapshots of a Faaslet, which means that the initialization code of a Faaslet is reduced. So just to give you an example of what the programming abstraction in Faasm looks like, so we have this concept of distributed data objects. So these are, they look like regular data types that a programmer would be familiar with, but in addition, they can be distributed across the serverless infrastructure. And so in general, the programmer would use standard programming construct that they are already familiar with. and then essentially the Faasm system would take care of the distribution. Different consistency levels between the data objects are supported in Faasm. So you can then specify essentially what the consistency requirements between this local state tier and the global state tier are. And this is an important requirement for our use cases in CloudButton because we have different consistency needs. So one of the strengths of the Faasm approach is that it's very efficient because we do not have to serialize data when we're moving it between the different state tiers. Because these are essentially memory regions that are directly accessible, we can share complex data structures in Faasm without having to express them as essentially serialized objects. And this is an important requirement when we want to take existing code, for example, in the genomics use case, because we want to use the data structures that have already been implemented and simply make them accessible to Faaslets when we deploy this particular use case using CloudButton. There are also mechanisms for fault tolerance here. So we can, for example, annotate functions to express the fault tolerance requirements, and this are then hints to the underlying runtime to then ensure that, for example, functions are restarted after they have failed. Okay, so in addition to the support that we have in Faasm for consistency and fault tolerance and the porting of existing code, I also want to talk about the support that we've developed on top of Faasm for running OpenMP applications. So OpenMP is quite important because it's pretty much the de facto standard for high-performance computing with parallelism. And so in the genomics use case, for example, the code base that we were given is written with OpenMP. So there is a large body of existing applications that use OpenMP, and for that reason, if we enable CloudButton to support OpenMP directly, we can take those existing applications and make it easy to then execute them using CloudButton in a serverless setting. So the basic idea is that we can take an OpenMP program, and so OpenMP programs are expressed using those pragma annotations where you, for example, specify that a particular section of your program should be executed in parallel. And so this is normally translated by the compiler to essentially OpenMP calls, as shown here on the slide. And then what we can do using our approach is that we intercept those calls, and we, based on those calls, we can, for example, understand what are the functions that should be executed as Faaslets in a serverless environment, and what is the shared state that they need to access. So we're converting essentially the functions to serverless functions, the shared state to essentially the local and global state that we can support through the Faasm framework. And based on that, we can then transparently execute OpenMP code in a serverless setting. So here we're taking advantage of the very efficient way how we can represent local state in WebAssembly and using Faasm. So for example, we can map the stack that is associated with different threads that were created by OpenMP directly to linear memory regions that exist on individual workers. And then for the distributed state, we're taking advantage of this global state tier. So we are transparently synchronizing local state from the workers, from the hosts, with the global state that we have available. So I want to share one performance result of this. So this is using the OpenMP support that we've implemented to run a distributed reduce operation. And the interesting thing about this plot is that on the x-axis, we're scaling the number of threads, And as we run out of cores on a particular host, we add additional hosts to that environment. And on the y-axis, we're reporting the throughput that we can achieve. And you can see that we get this very nice linear scaling behavior that initially we're scaling linearly as we utilize more threads per host. And then that linear scaling continues as we increase the number of hosts according to a scale-out model. And this is ideally the scaling behavior that you would like to have in a serverless environment, where you can sort of transparently add additional workers to your system and you get a linear performance benefit. Okay, so the last topic that I would like to talk about is the support for MPI. So why is that interesting? Well, so similar to how OpenMP is widely used by the HPC community for parallelizing applications within a single machine, MPI is the de facto framework that is used for cluster-based computing, where you want to distribute your computation across a larger number of servers within a cluster. And this is often used in code alongside OpenMP. And it's a platform-agnostic API, and it's often used for C, C++, and Fortran code, which are languages that we can support using Faasm on CloudButton. And again, when you look at available open source code, for example, on platforms such as GitHub, you can find a very large number of distributed applications that have been implemented using MPI. So if we have MPI support in CloudButton, it has the big advantage that suddenly there's a large body of existing code that we can then support. In addition, MPI has experienced a little bit of a renaissance in terms of the use for machine learning, and in particular deep learning. So when you look at modern deep learning frameworks such as TensorFlow, PyTorch, and MXNet, they have support for a distributed training library called Horovod, which is based on MPI. So MPI, beyond sort of traditional HPC, is also now increasingly being used in machine learning and deep learning. So how do we support MPI in CloudButton? Well, so we do this on top of the Faasm platform by effectively implementing an API that Faaslets can use that follows the regular MPI API. So we have point-to-point communication primitives such as MPI send, MPI receive. We also have collective API calls for broadcast, all reduce, and so on. And we have ways of providing remote memory access as well. So we're not supporting all of the MPI calls, but we're supporting a significant subset, which now enables us to already run a good chunk of different open source MPI programs. So there are various ways how MPI applications can communicate. So they can communicate using hardware queues and an RPC style communication mechanism. And they can also communicate more efficiently using distributed memory. And this can, for example, be implemented using RDMA. And so both of those communication mechanisms we can support in CloudButton using Faasm, because between FaasMPI runtime, we can have point-to-point message queues for message exchange, and then the Faasm state itself, essentially the local and global state tiers that I've described, can be used to implement the distributed state abstraction in MPI. So can we compete on raw performance with MPI? Well, so we're actually fairly close. I mean, the overhead that we can achieve, because we're using, for example, ahead of time compilation for WebAssembly, is pretty low, so we get good performance. And in particular, well, can we achieve the same scalability? And here it depends how efficiently the distributed state is implemented. But in general, we can show quite good scaling using this approach. Okay, this is all I wanted to present about Work Package 5. Thank you very much.